So yeah, this presentation, as you see, the title is about prospectivity mapping using machine learning. The goal of this presentation is not necessarily to do a dry theoretical presentation of what it is, even if there's a little bit of that, but it's also to address some of the questions that a lot of people have regarding these methods. So to address this, well, first, I'm coming from SRK Consulting, which is a technical consulting company for the mining industry. We're present in several countries, and we're working all over the world. So the way to address this topic in this presentation is through a series of questions, which I'll try to answer. The first being exactly what is prospectivity mapping? The second one is what is machine learning and how it is applied to prospectivity mapping? And then a few more specific questions on the approach, like is it a desktop only exploration tool? Is it a useless shiny gadget? Is it just data science applied without geological insight? I have a historical deposit in my property. Can we apply machine learning prospectivity mapping? My model has 99% accuracy. Does it mean it works? And finally, is prospectivity mapping the only way to use machine learning to support targeting? So yeah, after this presentation, I'll be open to any additional questions you might have. And let's start with what is exactly prospectivity mapping? Depending on where you come from in the world, it could also be called mineral potential mapping. These are the two same things. And basically it consists in trying to combine all available data in a specific area to estimate where you are the most likely to find deposits to support your targeting exercise. So mineral prospectivity model is basically, when you look at it mathematically, it's a function, an integration function that takes all of these geological information and try to combine it into one single map that will tell you where you're the most likely to find deposits. That's your output variable. Why do you want to do that? Well, prospectivity mapping, it's a predictive method. So you're not going to detect a deposit, but you're going to predict where you're the most likely to find one. It's best used at large scales, as explained on this diagram, even though sometimes at deposit scale it can be useful. And basically, it's used to reduce the size of your exploration search area in order to after be able to use direct detection methods like drilling, for example. So what do you do when you do prospectivity mapping? The output product usually is what's called a prospectivity map. You have an example right here. And prospectivity maps score the ground in terms of relative prospectivity within a grid of raster. So in each pixel of these maps, you have a score that goes from 0 to 1, 0 being the least prospective, 1 being the highest prospectivity. These scores are generally not probabilities, which means that if I have a score of 0.9, doesn't mean necessarily that I have a 90% chance of finding a deposit. Usually it's lower than that. It just means that it's one place where you're the most likely to find a deposit relative to an area with a prospectivity of 0.2, let's say. So why do we want to use prospectivity mapping? The first goal or the first use is to narrow down and rank the prospective ground. As I said, it's mainly applied at large scales. When you're an exploration company, you want to do that to target the ground where you want to conduct more focused exploration. It can be for claim selection, for example, property selection. When you're a geological survey for land management, jurisdictional promotion, or just to do an inventory of strategic resources you might have. And when you're an investor to choose where to invest, in which company, which hold, which ground. And what prospectivity mapping is not, it's not a direct deposit discovery tool, which means if you have a dot on the map, doesn't mean necessarily there'll be a deposit. And if there is one, you haven't discovered it yet, you need to drill and to prove it exists. It's definitely not an algorithm making a decision for you. At the end of the day, you're the one making generating targets, and it's definitely not an almighty tool. Geological interpretation is still a huge part of the process. So sorry for those who did want to find deposits without geology. We're not there yet. So how do you do prospectivity mapping? There's a general workflow, starting with having an exploration model. So it can be a metallogenic or deposit model, and generating exploration vectors. After that, you'll derive what's called predictor maps from the available data as proxy to these exploration vectors. Once you've done that, you'll integrate all of these predictor maps or evidential maps using a mathematical model, and we'll discuss that in more detail. And then you interpret the prospectivity maps that are generated in step 3 to generate targets. So let's look a little bit more in detail at these steps. The first one being the metallogenic and deposit model. This is standard in exploration. You want to know what exactly you're looking for. Can be a deposit model, can be the mineral system approach developed by the Australians. The idea is to get all the exploration vectors that are related to your deposit, so the conceptual exploration vectors. Once you've done that, you want to find where are these exploration vectors within my data. So you'll create what's called predictor maps or evidential maps. For example, if you know that you have to be close to intrusives to find deposits, you'll calculate the distance to the mapped intrusive. That's a good evidential map. You can calculate the distance to different types of faults. Or you can map the different lithological units, because you know that some units are more prospective than others. Or you can detect geochemical anomalies using geochemical analysis, because you know that some anomalies might be related to your deposits. Each one of these evidential maps can help you focus your targeting for deposits. And the idea of prospectivity mapping is to take all of these evidential maps together to generate one single map that will help you for targeting, which is your prospectivity map. So to integrate all of them together, you need a mathematical model to combine them and create a map that's highly correlated with the occurrence of deposits. So there's many approaches. There's not only machine learning, there's, for example, fuzzy logic, there's weight of evidence, there's plenty out there. Machine learning is just one of them. And the important parameters to take into account in all of these methods are the predictor map weights. Some are more important than others. Within one predictor map, the values weight between the different values in this map and the predictor's dependence relationship. Basically, to find a deposit, you need the combination of different factors for the deposit to occur. And this is what these dependence relationships are. So now that we know what prospectivity mapping is, what is machine learning for prospectivity? Well, machine learning is a data-driven approach that's based on the supervised training of the model, which means that you're not telling the model what to do, you're just providing the location of non-deposits, you're providing your geological data, and the model, the algorithm, will learn the relationship between the location of deposits and your geological data. So it's specifically adapted to regions or areas with complex deposit models. And when the data available is fairly large, and especially you need to have existing non-deposits. Without that, you can't train your model. Machine learning does not assume variable dependence. So it means it can learn very complex model with the different relationships between different input data sets. So how does a computer learn? If you see the prospectivity mapping problem as an equation, that would be this one. Y is equal f of x's. Our x's are our input predictor maps, and y is the location of deposits. You need to find a function that takes these maps and translate them in the location of your deposits, basically. And what machine learning does is it takes example of these x's and of our y's, our known deposits, and it tries to find the best function, the best approximation, f prime, to convert these x's into y. It's never perfect, but it tries to find the best function. And here's a simple example done here, where I have silica, magnesium, and I have basalt in red and andesite in blue. And I've asked a series of algorithms to try to find the best function to separate these basalts and these andesites. And you can see that different algorithms have different ways to answer this problem, some better than others. But you see that all of them try their best to separate these two groups. And when you do prospectivity mapping, it's the same thing. You try to separate deposits from non-deposits, basically. So how does a computer learn now for prospectivity mapping? Is basically you know the location of non-deposits and you provide this information to a computer along with all the available geological data. The algorithm will learn the relationship between your geology, your geochemistry, your geophysics, and the location of deposits. And when it's done, when the learning is done, you can say you have a trained machine, you have a model, a trained model. And now you can query it. When you give this geological information, you can ask, okay, where am I the most likely to find deposits? And very likely it's going to find existing deposits, but it's also very likely to find new areas. And these new areas are areas where you can generate targets. The advantage of this approach is that the algorithm is not biased by a deposit model. Maybe you think that faults are very important, but the algorithm doesn't know that. It's going to look at the data and objectively is going to assess all of this information against known deposits, quantitatively and objectively. So we say it's data-driven. However, the user chooses the input and interpret the results. So it's not 100% a machine that works here. We choose what to give. If we don't give the geochemistry, the algorithm won't be able to use it and it will be biased because of that, for example. So an important, one of the most important steps when training a machine learning algorithm is to validate and test it. Because maybe the algorithm, well, basically you want to know how good is your algorithm at detecting deposits, right? At detecting unknown deposits. So how do you do that? You hide some deposits to your algorithm and you'll see if it's good at discovering them, basically. It's done in two steps. The first one is called training and validating, where you'll have a training data set. You'll train an algorithm with this data set and you'll check with the validation if it's good or not. And you'll train many, many different algorithms with many different parameters against this validating data set. And you'll check which one works the best and you'll select this one. It will be called the optimized model. Once you have this optimized model, you want to know how good it is at finding hidden data. So you take your testing deposits, which have never been shown to the algorithm before, and you see how good the algorithm is at discovering them. If it's bad, it means the algorithm won't be able to discover new deposits. If it's good, it means the algorithm will be good at predicting the location of unknown deposits. So how do you know if an algorithm is good or bad? You need a metric, a scoring parameter. There's plenty out there in machine learning. I won't name all of them, but there's one which is a lot better and more adapted to the prospectivity mapping exercise. It's called the Auc Score. I'll go in a little bit more in detail about that because it's a very important parameter that allows you to know how good your algorithm works. So to calculate the Auc score, first you need to calculate the Auc curve. So the Auc, the receiver operating characteristic curve, it's built by plotting the false positive rate versus the true positive rate for all prospectivity values. So let's say I generate my prospectivity map and I select the 10% highest prospective ground that would be here on the x-axis. And I see that within this 10% of the ground, I have 70% of my deposits. If I select 40% more prospective ground, I have 90% of the deposits, and so on and so forth. So the more you increase your prospective ground, the more deposits you'll have, but it will be larger, so not ideal for exploration. What you want ideally is a Auc curve that's very steep, goes high, reaches the 100%, and then is flat. It means your algorithm is really good. If your Auc curve is a line like that, it means your algorithm is really bad. It's as good as a random prediction. So you want these steep curves, sorry. Now, how do you extract a metric from this curve? You calculate what's called the AUC score, or area under the curve. And very simply, it's you calculate the area on this diagram, the area below the curve that you have drawn. So for example, the area below this random prediction curve, it's 0.5 because half of the diagram is below this curve. For this AUC curve, the AUC is 0.85 because 85% of your area is below this curve. And ideally, you want a score very close to 0.9, and 0.5 means that your model is very bad, basically. So now I'll answer a few questions related to these exercises. The first one being, is it a desktop only exploration tool? We have a lot of field geologists saying that we're trying to replace them. That's totally untrue. And here's a good example of why. You have two rock curves here with the associated AUC score. So both are for the same project, for one like prospectivity analysis on a project. One rock curve, the best one is when I include field-derived data to the model. So geochemical sampling, geological mapping, etc. We have a really good rock curve. When I put only the remote sensing data, I only have 0.79. It's not bad, but it's not as good. So field work and data collection is still definitely part of the discovery process. And what prospectivity mapping does is taking data, making interpretation from them. You need good data to get good interpretations. So you definitely need field data. Another big evidence of why prospectivity mapping is not a desktop-only exploration tool. We have a prospectivity map here. The green points are known occurrences. And if I want to do a targeting exercise here, maybe I'll look at what looks like a fault hinge here. It's very high prospectivity, right? So that's interesting. Did I discover a deposit? No, I just generated a target. Maybe there's something, maybe not. And I need to do field work here to make a discovery. And if I don't do good field work, if I don't drill the right direction, I might not find something that's there. So you can't do a discovery just using machine learning. It's just one tool that will help you go and make your discovery. Now, the next question is it a shiny, useless gadget? It's something that sometimes we hear, how to say, technology reluctant geologists say, and that's a fair question. But how do you want to do objective, reliable, and quantitative targeting when you have, for example, 15 exploration datasets that go from satellite imagery to geological mapping, and you want to generate targets? A geologist, even with a GIS software, won't be able to just look at all of these layers and make reliable targets. That's too many of them. When you want to integrate a lot of data together to have something reliable and quantitative, you need a mathematical model, you need prospectivity mapping, and machine learning is a good way to do this prospectivity mapping exercise, even though others are available as well. And a good evidence that this is not just a shiny, useless gadget, it's just looking at the numbers. Oh, sorry, my mouse, is so it's back. So you see on the left, the diagram on the left shows the result of a prospectivity mapping exercise for one project, and you have the distribution, the density distribution of the ground in blue, which has not known deposits, and in orange, the ground which has known deposits. And you can see that the deposits are mainly in the high prospectivity ground, and that the areas with unknown deposits are mainly with low prospectivity score, just a little part of them being at high prospectivity score. So you know that deposits have high prospectivity score and that you're more likely to find deposits in this high prospectivity score ground. So this little part of the data which is in higher prospectivity scores. This table here explains the exact same thing. You have a bins of prospectivity scores for another project, and you see that if you have low prospectivity, there is no known deposits within these areas. But when you're looking at pixels that have higher prospectivity score, so let's say from 0.9 to 1, you have a 1.8% chance to have in one pixel. If I remember well, it's a 250 so no, it's even a quarter of a square kilometer per pixel. In each quarter of a square kilometer, you have 1.8% chance of finding a deposit. So you can already remove a lot of your ground with low prospectivity and focus your exploration on high prospectivity ground. So it's definitely a useful tool. So is it just data science applied without geological insight? There's a really good example here of what happens when you include raw data and what happens when you include interpreted high quality data. Here's an example from another project where I calculated the individual AUC, so the AUC score, for different layers. And these layers are in two groups. At the bottom, you have geophysical surveys, non-interpreted, just the raw data, so gravity, vertical derivative, and mag, and same thing, the vertical derivative. And only the gravity survey has a fairly high score. But when you take the same data sets, so all of the above in green are from the same data sets, but they are interpreted. You have a lot more data sets with higher AUC scores. And a very good example is the lithological interpretation from the MAC survey. So it's a geologist who does this interpretation. This has a AUC score of 0.75. This is the best among all of these data sets. While when you look at the MAC data by itself, it's close to 0.5. It's useless. So you need a geologist. You need someone who understands the deposit type, who understands what you're looking for, and who is able to make good interpretation to interpret this data to provide something that's reliable and useful to the model. So it's not just data science. If you're just a data scientist, you'll go nowhere. You need good geological insights to be able to generate good models. And there's a large number of evidential maps that require interpretation steps. When you want to extract prospective sets of faults, you have to understand the structural model and have a good one. Specific lithologies or combination of lithologies, you need to understand which lithologies are better hosts or more prospective for your deposits. And when you're looking at geochemical data, you have to be able to do proper geochemical processing before you give this data to an algorithm. Otherwise, the data will be useless. Now, the next question is, what happens if I have a historical deposit in my property? Can we apply machine learning prospectivity mapping? And this is a question I get often. I was asked that by a client just 2 weeks ago. And unfortunately, the answer is no. If other service companies say they can use artificial intelligence and machine learning to do targeting using just one deposit, be very careful, because in most of the cases, it's not possible. And here's the explanation why. If you have plenty of deposits, the algorithm will be able to learn your geological model exactly with looking at the differences between the different deposits and finding the common points. But if you have only one deposit, the algorithm will not be able to compare and to learn properly. So for example, if your deposit is cross-cut by a mafic dike, doesn't have anything to do for the deposit, but there's a mafic dike here by chance. What the algorithm is going to learn is mafic dike is good for prospectivity. It will tell you there are deposits every time you have mafic dikes. It's wrong, but it didn't have enough examples to be able to do a proper model. And this diagram here gives a good explanation of what happens when you reduce the number of training deposits. When you start to go below 40, the AUC score will decrease quite drastically. And even if you go below 10, it will be very, very high decrease in AUC score. So you don't want to train with few deposits, and one, it's definitely not enough to train. The next one is my model has 99% accuracy. Does it mean it works? I've seen some out there, models with 99% accuracy. Unfortunately, it means that the person usually it means that the person doing the model don't know what they're doing. If the model is not tested on truly hidden and independent data, the metric used, whether it is accuracy or AUC, will suggest unrealistically high performance. And I give an example here with two projects, and I've tested the AUC scores using different methods. The first one, something you should never do, is to test on training data. So I give the same data to test that I gave the algorithm to train. And the algorithm indeed finds very easily the deposit it was shown before, which makes sense, but it doesn't mean it's going to be able to find new deposits. So I used a more conventional methods of testing on random test data. So I kept some deposits hidden, never show them, randomly selected these deposits, and then tested the algorithm against that. And you can see the AUC score is a lot lower. And finally, I've tested on spatially distinct test data. So this time I've cut my map in two. I've trained my algorithm on one part of the map and tested it on the other part of the map. And you can see the AUC score is a little bit lower for project 1 and significantly lower for project 2. So what happens is that usually deposits are clustered. And if you take one deposit from a cluster for training and the other deposit from the same cluster for testing, the algorithm will have learned very well to map deposits within this cluster. Doesn't mean it will be able to find a new cluster of deposits, which is usually what we want to do in exploration. And so if you really separate your training and your testing data sets, you might have lower scores. And if you want to find the best model, you should use these testing methods to be able to find the model that will be the best at detecting hidden deposits. So the user should always make sure a sound testing method was used. And in general, in machine learning, when you have 99% accuracy, generally means you have done something wrong. So finally, is prospectivity mapping the only way to use machine learning to support targeting? Well, machine learning is a field that groups a wide range of techniques that allows to make prediction based on example data. And overall, prospectivity mapping is a great tool, but there's plenty out there that people don't know about. There's many applications based on many different methods and algorithms. Prospectivity mapping is probably the most obvious because it's a dream for everyone to take all of the data and generate targets. But there are many highly valuable other applications, such as lithological or iteration mapping, automated core logging, geological modeling, and I probably forget a lot of them. So I have a few examples here just to give you an idea of what's possible and to show that there's a lot of opportunities with machine learning in general. This first one, so this is not from SRK, it's from another company who allowed me to use the slides, Journal Solutions. They used some high resolution MAC data to train a model to recognize, so to be able from low resolution MAC data to be able to interpret the high resolution. So how does it look like? You have on the top left, the low resolution MAC data, and on the right, what the algorithm interprets as what should be the high resolution. And on the bottom, the real high resolution MAC data. So as you can see, this algorithm is able to add some accuracy to your geophysical data, which can be really useful when you only have historical low resolution data. Another example for geochemical mapping, this is from an academic paper, where you have on the left interpolation of geochemical data using ordinary kriging. It's quite fuzzy, it's because there's not a lot of samples. And on the right, you have the same interpolation of the geochemical data, but this time you combine with remote sensing data and machine learning. So they have added geophysics, elevation models, remote sensing, and combine all of that in the machine learning model to interpret the geochemistry. And you can see you have a data set which have a lot more granularity and, which is a lot easier to interpret for a geologist. You can use machine learning in the mining environment to use your geological logging or your geochemistry to generate alteration, geology, and to be able to support your 3D modeling work. And finally, another really cool application is automatic core logging. Machine learning can also take images, and you can, from your core images, generate things such as mapping of veins. So here on the left, you have the core image. On the right, you have the machine learning interpretation. So it's the algorithm which has mapped to the pixel the location of veins, yellow being quartz vein, blue being not a quartz vein. And you can extract this information, put it in a 3D model, like here in Leapfrog, where we have put the location of and density of veins in space. And you can see the distribution of your veins in 3D, which is a lot harder to do when logging because it's a very boring process, a very repetitive and tedious process to log every single quartz vein manually. So to conclude, machine learning for mineral prospectivity, does it generate targets? We've seen that it's not the case. It's a tool that helps the geologist generate targets. It's definitely not a treasure map. What it is just a tool that helps us integrate the available data into a single quantitative map that helps us target. It reduces subjectivity, and it's a good tool to validate an exploration model. If the algorithm says that the data that we put in is not useful for exploration, probably we have the wrong exploration model, we're using the wrong exploration vectors, and we should think again. And it's a good tool as well to see what are the data gaps and to go back in the field, collect this data, and be able to have a better model. So machine learning is, I think, definitely a powerful tool applied to prospectivity mapping. It works specifically in data-rich environment with non-existing deposits. At the end of the day, it's a new tool. It's not a revolution, it's an innovation. And at the end of the day, the available data, the initial conceptual models, the conception of evidential maps, so all the work you do before you do prospectivity mapping is the most important, parameters. It's not your algorithm, it's not your computer, it's the data you have, how you prepare it, how you interpret it, that at the end of the day will help you generate these targets. And as we've seen, machine learning is definitely not limited to prospectivity mapping. There's plenty of applications out there in exploration, and I'm sure in the next few years we'll see plenty more applications coming. So here are some references that were used in this presentation. Don't hesitate to contact me if you want more references on the subject. And here's my email. So thanks a lot, and I'm open to questions.
Thank you, Antoine. It was a outstanding presentation. So please feel free to ask. We have already some questions from Victor Torres. Great presentation. What do you think about self-organizing maps, ACE on IM or TSNE options in iOS?
Okay, so I didn't go into much detail about all the different algorithms of machine learning. There are basically two classes of machine learning algorithms. There's what's called supervised learning, which is you know what you're looking for. So that's what we use here. We know we're looking for deposits. We have example of deposits. And then you have unsupervised learning, which is also called clustering, which is basically you give data to, the data just to the algorithm, and the algorithm will try to find the groups, the patterns within this data. Self-organizing maps are one of these clustering or unsupervised learning algorithm. It's a very powerful one and very helpful to help find the different groups in your data. It's not going to be necessarily very good at finding your outliers. So if you're looking for like very high gold value related to your deposit, it's not likely to find that. But if you want, for example, to find your different lithologies or different types of alteration, this is going to be a very powerful, very useful tool.
Right.
Yeah, in general and in IOGAS in particular, but yeah, in general.
Right. Frankie said, thank you for this very interesting talk. How do you generate known deposits?
Okay, so it really depends of where you are in the world. In some places, you have already had a lot of mining history, so you just take the existing mines. If something has been mined, it's been economical, and it's very likely to still be economical. So it's a good representation of what you're looking for. In places where there's been a lot less exploration or a lot less mining activity, you'll have to go with occurrences. So if you know that underground here, there is evidences of orogenic gold, not necessarily a deposit, we don't know yet, but there's evidences of orogenic gold, this is a good training point. But yeah, you'll need this training point in your area of interest. If you're somewhere where nothing has been discovered yet, well, tough luck, you won't be able to use machine learning because there's no way of training your model.
Right. You already said what you don't use your statistic for your mapping compared to machine learning. Mineralogical data have regionality, so your statistics should give a better results.
So not necessarily. So geostatistics is a very good tool for interpolation. So if you look at it in the machine learning way of seeing things, it's basically your input values are your X and Y, your location in space, and your output is, for example, your gold grade. But what machine learning does is that it takes other variables. It can be your other geochemical values, it can be your geophysics, it can be a geological model, and it will use this information to make a better or to make a different interpolation. And in many cases, it's going to be better. However, machine learning, for example, for resource estimation, is not necessarily better because geostatistics in this case are better. But if you want to use, so for example, the example I had above, this example here, where ordinary kriging, which is a geostatistical method, doesn't take into account the remote sensing data, geophysical data. And when you add this information using machine learning, you'll have better results. So depending on the problem, sometimes geostatistics will be better. Sometimes it's going to be machine learning. It really depends on what you're trying to do.
Great. Maria asks, is there a rule of thumb for a minimum ratio between amount of deposit area unit?
I would say, okay, generally, I will not use machine learning if I have less, or I'll never do machine learning if I have less than 10 deposits. If I have more than that, usually for a project, what I'll tell, so if I have, let's say, between 10 and 40 deposits, I'll tell the client, okay, I'm going to try machine learning and I'm going to try another method, for example, fuzzy logic, which doesn't need training method, and I'll take the one that works best. Because sometimes there's not enough deposit for machine learning, so I'll have to use the other methods. If I have more than 40 deposits that are not too clustered, usually there'll be good results. Yeah, but that's a rule of thumb, and it will depend on the complexity of what you're looking for. So it's very general numbers, and usually you have to test to see if it works or not, basically.
Right. Guilherme said, thanks for the talk. In your experience, do you believe that transforming compositional data, positive values with a constant sum geochemical data is a crucial step in using machine learning techniques?
So compositional data, that's a very complicated topic. So it will, sorry, but the answer won't be clear. It depends on the algorithm you use. So for example, the algorithm I use for a prospectivity mapping, it's called random forest. It's a non-parametric algorithm, so it doesn't care about how the data is organized. It will be able to see the patterns in the data, whatever it is. And I think, there's a paper I published where I compared the use of different algorithms with compositional data that's been non-treated and then treated for so opened. So I removed the compositional patterns, and it didn't do any difference. But some other algorithms will be strongly affected by compositional data. So for example, a super vector machine or unsupervised method like, for example, the PCA, principal component analysis. It's better to open your data before you do that. So there are different ways to do that. For example, centered log ratios before you use, and you'll see that if you don't open your data, if your data is still compositional, you'll have weird results.
Great. And Mireia said, thank you, Antoine, for doing a great presentation and clarified this about machine learning. Please, can you explain a bit more about your statistic? How are you applying to your project? Because mostly of your interpolate models that have you show are kriging.
Yeah, so I'm not a geostatistician, so I can't comment too much on that. There's a lot of geostatistical methods out there. Kriging, co-kriging, simulations, multi-point geostatistics. Depending on what's your problem, you might want to use different. But yeah, it's not my domain, so I would not comment too much on that. But yeah, machine learning and geostatistics are two different fields. Sometimes they can accomplish, like solve the same problems, but in some cases, you're a lot better using geostatistics, and in some other cases, you're a lot better using machine learning.
Andrew Paul said, thanks, Antoine. Great summary. Have you tested ML-based interpretation, such as ML lithology interpretation, in the same way you look at the high AUC of human interpreted lithology?
That's a good question. No, I've never compared. I don't remember. I don't remember comparing. No, I don't remember comparing like a machine learning based lithological interpretation with a human based one. Usually is you have one or the other. If you have a good human lithological interpretation, you don't need machine learning to generate it. And if you use machine learning, well, it means that you didn't have the human one, and so you can't compare the two.
A question from Franklin. Do you think that transforming continuous predictor maps into categories is useful for machine learning for prospectivity mapping?
Yeah, okay, there's no yes or no for this question. It's all about granularity and what's called overfitting. So I didn't go into this level of detail, but basically what can happen if you don't control your machine learning algorithm is that it's going to, for example, you have a goal, or let's say distance from a fault that goes from 0 to 10 kilometers. And then you have, so it's a continuous value, right? And if your algorithm is not very well tuned, it can say, oh, there's a deposit at 0.55 kilometer and one other deposit at 0.66 kilometers. So prospective ground is only at 0.55 kilometer and only at 0.66 kilometers from a fault. Doesn't work. So you want, for example, to categorize your values in distance from 0 to 1,000 meters. So from 0 to 1 kilometer, from 1 to 2 kilometers, from 2 to 3. And this way the algorithm won't be looking too much into detail. It will look at the bigger picture and make better predictions. So it can be useful sometimes, but if you're using the right algorithms, your algorithms shouldn't have this type of behavior, and you shouldn't have to categorize your data. And the issue with categorizing is that you lose a little bit of detail, and your maps won't be as granular or as like there won't be as much variations in your map. So it won't be necessarily such a good map. So in some cases, it's better to categorize, but in other cases, it's not. Sorry if there wasn't a clear answer, but yeah, depends on the cases.
We're still receiving more questions. Ella said, thanks for the talk. Can I ask which software or programming language do you usually use for machine learning?
Okay, so personally, I use mainly Python, so it's a programming language. In some cases, to do simple things quickly, I use a software called Orange. And for really big data problems, I use Microsoft Azure machine learning platform combined with Python. But it's just what I use. There's plenty of other tools out there. So in terms of programming languages, I recommend learning a programming language if you want to do machine learning, because this way you have no limits. You can do whatever you want. So there's Python, there's R, there's MATLAB as well. And there are a few others, but the main ones are these three guys. There's a lot of software. Some are open source, some are you have to pay for them. They are a lot easier to use, but very quickly you want to do something and you can't because there's limitations to software. Well, when you code, the limitation is your imagination, basically. And then there are the cloud platforms. So Microsoft Azure, there's the Google Cloud, and there's Amazon Web Services, and there's probably others out there which provide both the computing power and the machine learning tools. So there's plenty out there with variable advantages and disadvantages.
Great. Victor Torres asks, any successful discovery story with prospectivity maps?
Yeah, there's a few. There's so the one with like you need a publicly listed company to like make publications about that. But there's a Goldspot, for example. They have had a few successes. So targets that were generated, and when they drill, there was something, and nothing, as far as I'm aware, has become a mine deposit yet. But yeah, they have made significant discoveries. There's another company in Australia. What's the name? I forgot the name, but yeah, they use deep learning and they have discovered a few occurrences as well. But I don't think anything has become a deposit yet. So yeah, there are successes. I think it's still, it's not a young technology, but it's only recently that people start to use it a lot. So we'll come to things becoming deposits probably in the future. But one point I want to emphasize is that I think it's incorrect to say there's a discovery using prospectivity mapping. It's just prospectivity mapping was one of the tools that led to discovery. It means that people, before collecting the right data, got the right geological model, and then of course they did the right prospectivity mapping, and they did the right field work. So it's a combination of things. It's not just I use prospectivity mapping and discovered the deposit. It's one tool that was used in the process.
Awesome. Mireya Terrones asks, all the algorithms that have you used for your projects are scripted in a software now, or do you use any other?
So generally, the algorithms are used. So when I code in Python, I use machine learning packages. So it's all open source public algorithms. Everything I use is has been tools basically made by people and free on the internet. People contributing, improving them every day. So for example, in Python, there's the scikit-learn package, which has a lot of machine learning tools for sorry, I'll go down. Yeah, for this automated core logging, that's actually a pretty cool story here. What I use here, you know, these algorithms that detect cats and dogs on photographs, or that will tell you there's a car or a bike. Basically, I took one of these that was developed by Facebook, so like a very good, very high quality algorithm. It's free on the internet. I used it and I tuned it, just modified it a little bit to look at rocks. So it's all things that are open source available for free on the internet. You just need to learn how to use them properly, basically.
Right. So Romero said, thank you for your great presentation. For the fuzzy operation, what is the fundamental concept for defining the gamma value?
Oh, for the fuzzy, the gamma value is a tough one. I don't remember the, so for everyone to follow, that's a little bit earlier, that's here. Yeah, this gamma value, it's, so the fuzzy R, you have two maps, and you take the highest value of the two maps and you create a map. The fuzzy end, it's you take the lowest value of two maps and you create a map. The fuzzy gamma, it's something in between. So it uses a combination of multiplications and additions. I don't remember the exact formula, but yeah, it's if on Google you type fuzzy gamma ArcGIS, you'll find a website from the ArcGIS software which explains the exact formula of the fuzzy gamma. But it's something in between the fuzzy end and the fuzzy R.
Marco Acevedo asks, what tool are you using for image registration or georeferencing?
For the image, so you, for this application or for prospectivity mapping?
He didn't specify this. Just what tool are you using for image registration or georeferencing?
Oh, georeferencing. I use normal GIS software. So I work mainly on QGIS, but there's also ArcGIS, ArcMap, whatever you want to use. It's yeah.
Okay, we have our last two questions from Ronald Calupe. Is it possible to give greater weight to a layer, lithology, structural alteration, similar to the multivariable method, or each layer has the same weight in machine learning?
So in machine learning, it's the algorithm which decides the weight of each layer. And that's what makes it powerful, is that we can't bias it. We give the data, it decides by itself the weight of each variable. So there is a weight for each layer, but we don't decide it. It's the algorithm which is going to decide it. So if you want to force a weight, you have to use a knowledge-driven approach, like a fuzzy logic, for example. It's a different approach.
His second question is, do you have an example of discovery by this method?
Yeah, well, I already answered this question. Yeah, there are a few targets that were successful and with discoveries of significant mineralization. But nothing has become a deposit yet. But yeah, as I was saying, so two things. First, it's fairly recent that people use it that much. So I guess some things will become deposits, some discoveries will become deposits in the future. And again, it's a tool. It was part of the discovery process, but we can't say, or I don't like to say, machine learning discovered the deposit. It's not true. It was just part of the process to make the discovery.
Okay, and here's another question from Mireia. Where the image core come from? Core scan, e-logger?
No, from a simple camera. So it's not like a hyperspectral camera or whatever. It's just like any exploration or any mining company should take good quality photos of their core just as a quality process. That's just it. It's RGB, so like with a regular camera photograph, and we can work with it. So it's fairly cheap compared to all this hyperspectral data. But if you have hyperspectral images, that's even better because you have a lot more data, more high quality data, so you can get better predictions.
Okay, one more question. Well, still coming. So, Isaac Montalban asks if you have used hyperspectral cam.
Never, but if you have a project where you want to use it, I'm definitely interested. That's something I want to do. So yeah, after working with RGB images, the next step for me will be to work on hyperspectral data, definitely.
Giorgio Sadorato asks, is possible to have the same model such as the SEDEX you showed for other models?
Is it possible to have the same model?
Such as the SEDEX you show for other models, sediment deposit?
Oh, I guess the question was if you train a deposit somewhere and you can apply it somewhere else.
Yeah.
So you would have asked me this question 2 months ago. I would have said, no, it's not possible. But recently, there's a PhD student called Francisca Maepa, who managed to do that. So she trained a model somewhere in the ABTB and then applied this model somewhere else and got really good results. So yeah, it's possible, but you need to make sure you have the same geological context, the same type of rocks, and the same type of data to be able to train a model.
Okay, and our last question for today is from Juan Jaimes. Is there any reference on that core information?
For the automated core logging?
Yeah.
No, it's fairly recent technology, and so we are at SRK. We're not the only one doing that. There are other service companies, just a few, like just probably 3 or 5 on the planet who can do that. But there's, as far as I'm aware, there's not really much scientific publications on the subject, no. So yeah, if you're interested, just if you have questions on the subject, you can contact me. But I don't think there's, no, that's not true. There's been some publications, but not like applications to the level of that. Yeah, mapping as precisely veins, for example, that's yeah, that's never been published. I don't think so.
Great. Thank you so much, Antoine. It was a great presentation. And thank you everybody for joining us. So stay tuned. We have our third webinar and it will be given by Dr. Robert Lee about porphyry deposits. So stay tuned and we hope to see you there. Thank you so much. Cheers, everyone.